Hello everyone. So my name is Professor Robert Lancaster from Swansea University, and my talk today will be looking at the influence of surface finish and build orientation on the low cycle fatigue performance of laser powder bed fused stainless steel 316L. I want to quickly acknowledge some of the co-authors of this work. In particular, Will Beard, as a large part of this research was undertaken in his doctoral project, which was sponsored by Rolls-Royce. So a quick introduction to set the scene. As we all know, additive manufacturing, or AM, is a near net shape manufacturing process that's receiving a significant increase in global attention from all manner of different industrial sectors, one of which is the nuclear sector, who are now looking to benefit from the many advantages that AM processes have to offer. So some of these include unrivaled design freedom, to allow the manufacture of highly intricate and complex components, which of course is a major plus point for design engineers. The production of near net shaped structures, which is great for reducing material wastage, and also it eliminates the need for expensive tooling such as molds for casting, and as such it reduces the amount of processing steps. And AM also allows fewer joining regions, removing possible stress radiation features and interfaces. So one such AM process is laser powder bed fusion, a process typically used for component manufacture. And the process builds a three-dimensional part in a sequential layer-by-layer basis by utilizing a high-energy laser heat source to selectively melt and fuse two-dimensional slices of a component. The base plate upon which the powder is spread then retracts, fresh powder is laid, and the process is repeated then until the final geometry is fabricated. So as AM has become more and more popular, so has the understanding of the mechanical properties of AM manufactured materials. However, this has predominantly been limited to static loading conditions, with the understanding of dynamic cyclic load in the form of fatigue not yet fully understood. Yet these dynamic cyclic loading conditions are a requirement for many critical applications. So when considering the fatigue behavior of AM materials, surface roughness also plays a key role, since the surface roughness of as-built LPBF material is inherently coarse, yet removing the post-build machining process could both reduce manufacturing time and cost. So my talk today will be looking at the influence of surface finish on the low cycle fatigue performance of LPBF manufactured material. The material of choice in this project was stainless steel 316L. So 316L is an austenitic grade of stainless steel, which typically has a high nickel content and moderate addition of chromium to aid its corrosion resistance. For the purposes of this work, we looked at LPBF 316L manufactured in two alternative build directions. So firstly, the vertical orientation, or 90 degrees, and also the 45-degree orientation, to try and understand how build orientation also affects the microstructure and surface finish in different orientations. So a set of LCF specimens were built in the two different build orientations on an EOS M290 machine using gas atomized powder with a particle size distribution ranging from 5 to 60 microns, with a full composition given in the table to the right of the screen. Post-manufacture, all the specimens are subject to hot isostatic pressing for a few hours at an elevated temperature above the solution temperature to alleviate any porosity left over from the processing steps. In terms of the microstructure, what we got here are the EBSD maps for both the vertical material, so the top images, and the 45-degree samples given at the bottom. So in either case, the grain boundary maps for each variant are given to the left, and the inverse pole figure map to the right. In both cases, the material is predominantly made up of an austenitic FCC microstructure with very, very small amount of retained BCC ferrite distributed at some of the grain boundaries. And then in both orientations, an elongated grain structure is also apparent on the face parallel to the build direction, resulting from the epitaxial grain growth during manufacture, with an equiax grain morphology, as expected, seen on the perpendicular face. The vertical build can be seen to be highly textured in the 101 direction, and as a result of the hipping procedure, the material is now fully dense, with no evidence of porosity seen in either material. Prior to testing, to understand and quantify the surface roughness profiles of the different surface finishes, an Alacona infinite focus G5 microscope was used to record the roughness related parameters, each of which are defined in the table below. So several parameters were measured, so we can identify which of the parameters appear to have the greatest influence on fatigue performance. So for this analysis, a 5 times magnification was used throughout, with single measurements recorded at intervals of 0 degrees, 90 degrees, 180 degrees, and 270 degrees. So every quarter moon junction to give us a full picture. Also, just a note that due to this significant form in the image field 3D dataset, the true form of the specimen geometry is removed to obtain relevant reference values. So on to the mechanical testing. In this research, the specimens are subjected to string control LCF testing in accordance to ASTM E606. The specimens are manufactured in the 2 build directions and finished with a series of different surface finishes on the gauge section. So this included the ASTM longitudinal polish, a circumferential polish, deliberate machined finish with an RA of 3.2 and 6.4 microns, a vibratory mass finish, and also a series of specimens were retained in the as-built condition. All tests were conducted at ambient room temperature under controlled laboratory conditions, and a strain rate of 0.4 and an R ratio of -1 was used throughout. A series of maximum applied strain values were used to generate full SN curve responses across the different build orientations and surface finishes, and failure was deemed to have occurred after a 25% drop in the peak load had been surpassed. So moving on to the results. Firstly, looking at the surface roughness values, firstly considering the vertical specimens given in the top table. And as we can see, looking at the RA values as the main parameter here, the as-built specimen has the largest value, so the worst finish, or the specimen with the highest average of absolute values of the profile height deviations from the mean line. This is then followed by the deliberate RA finish of 6.4, then 3.2, then the remaining 4 finishes are quite similar. This is very similar for the 45-degree samples, where again the as-built samples have by far the roughest finish, with the rest of the finishes behaving relatively similar. For these though, the RP value, or the maximum profile peak, has more of an established ordering, with the longitudinal finish the worst, followed by the circumferential polish, and then the 3 different mass finishing conditions, with the highest micron finish, as expected, have the most optimal finish. Looking at some of the LCF results now, so given here are the SN curves for the vertically built and 45-degree samples. As you can see for the vertically built specimens, so given in the graph to the left, as expected, the as-built and deliberately machined specimens offer the worst LCF response, with the mass finishing vibratory procedures and the ASTM longitudinal finishes offering the best response at the lower and higher applied strain levels respectively. Then for the 45-degree orientation, so the graph to the right, again the as-built surface is the worst performing variant, with the ASTM longitudinal polish and the mass finishing procedures showing the best life. So it very much seems that surface finishes are having a direct influence on LCF performance, irrespective of the build orientation of the sample. Looking at the fatigue results in a little more depth, what we have here are 2 separate plots showing the evolution of maximum and minimum stress across the 2 build orientations, with the verticals to the left and the 45s to the right. In each case, plotted here, these are the specimens of each of the different surface finishes, which were subject to the same maximum strain value, which is 0.6%. The graphs show that in all cases, there is a small, almost minute degree of hardening in the first couple of cycles, which is actually quite difficult to see, which quickly succumbs to a period of cyclic softening, which takes place over 100 cycles or so, after which the stress flattens off quite nicely to a very stabilized condition. In both cases, the as-built specimen exhibited the smallest stabilized stress range. Looking at the hysteresis stress-strain loop response, what we have here are the first monotonic loading cycles for each of the different finishes under the 2 different build orientations, with again the verticals to the left and the 45s to the right. Again, all specimens were subjected to a maximum strain of 0.6%, and the graphs show that the Young's modulus values are pretty consistent throughout, with the as-built specimens given in red here appearing to yield first, as would be expected when looking at the stress evolution plots on the previous slide. So then look at the same plots now under the stabilized or half-life condition, and as expected, the as-built specimens display the lowest stabilized stress range across the 2 orientations, plus the greatest level of plasticity when looking at the width of the loops, which means it is experiencing the largest level of permanent deformation upon the application of each fatigue cycle. A quick look at some of the fracture surfaces, and given here the fracture surfaces for the vertical specimens, and despite the change in surface finish, there's not a massive difference in the nature of the fracture modes. The reason for this is also strongly attributed to the loading ratio of -1, which of course introduces a compressive portion to the fatigue cycle, which can effectively eradicate many indicative fatigue features on the surface, such as striations and crack growth behavior. We can make up the initiation sites though, as highlighted by the red boxes, and in each case, nucleation appears to have started near or at the surface, which of course is a good indication that the material is fully consolidated with minimal evidence of failure originating from any subsurface anomalies. And it's also a similar case as well for the 45s, where there's minimal difference or anything of note across the different fracture surfaces as given here. So with the generation of quite a large bank of data, we also looked at some empirical methods in an attempt to like the different finishes and orientations. So to do this, we had some discussions of Nima Shamzai from Auburn University in the US and implemented a blended Coffin-Manson-Basquin approach. So firstly, using the stabilized stress strain loops, we measured the modulus values to help us calculate the elastic strain amplitude. With this, we could calculate the plastic strain amplitude values, which of course is more akin to LCF conditions, by simply subtracting the elastic from the total. Then we bring in the Coffin-Manson equation, which is the plastic strain amplitude is equal to the fatigue ductility coefficient multiplied by 2 times your fatigue life to the power of a fatigue ductility exponent. These coefficients and exponents can be calculated by plotting the plastic strain amplitude across your fatigue life values, times them by 2, and then using a log-log axes. For HCF conditions, so fatigue data beyond 100,000 fatigue cycles, where the material is predominantly deforming in an elastic manner, the Basquin approach can be used, which is calculated by the stress amplitude being equal to the fatigue strength coefficient multiplied by 2 times your fatigue life to the power of a fatigue strength exponent. So like for Coffin-Manson, these coefficients and exponents can be calculated by plotting the stress amplitude against your fatigue life values, multiplied by 2, and then using log-log axes. Once determined, these values can then be substituted into this long equation here in the last but one bullet point. To produce the data fits given in the 2 graphs given here. So here we have the vertical results to the left and the 45s to the right. So the points on the graphs are the original data points gathered from the mechanical tests, and the curves are the ones generated from the empirical calculations. As you can see, the curves are pretty good throughout, which of course is very pleasing, but it also gives us a very decent indication of what the fatigue lives would be like under higher and lower strain values than those used in the tests. Although lacking in the elastically dominated high cycle fatigue range, we did take some values from literature, as given by the darker coloured series, and they match up with the plots quite well, which of course, again, is quite pleasing. Of course, though, caution does need to be taken to jump to any kind of bold conclusions, and tests would still need to be carried out, particularly under the HCF conditions, to flesh up these curves a little, but the fits do look very promising indeed. So to conclude, the LCF behaviour of vertical and 45-degree orientated LPBF stainless steel 316L was assessed in a variety of conventional and novel surface finish conditions. Results showed that the as-built vertical LPBF material displayed the greatest reduction in fatigue life, with the ASTM longitudinal polish and the mass finishing procedures showing the longest fatigue lives. Alacona surface profilometry was completed with various roughness values measured, showing the as-built surface to offer the worst finish, followed by the deliberate RA values. Hysteresis loop analysis showed that the as-built materials seemed to yield earlier, and this led to the lowest stabilized stress range being observed in the as-built variants, and also the greatest level of plasticity, which contributed towards the lower lives of the specimens with this finish. The Coffin-Manson Basquin plots have also been completed for all variants in both vertical and 45-degree orientations, and the fits show good agreement with the data generated, but again, more data still needs to be gathered to really iron out the robustness of these curves. Finally, a bit of future work, and we've been in discussion with Nima Shamsai at Auburn, and we're looking to add another variable to the mix and looking at if different AEM machines have an effect on LCF performance on samples built in the two different build orientations and subjected to the different surface finish types. So that brings an end to my talk, and thank you very much for listening.